Good afternoon. I'm David Lucsanyi, and I will talk about Puli Lunar Water Snooper, the payload instrument we are currently developing at Puli Space Technologies, which is an in situ water mapping payload for lunar surface missions. I'm the lead payload scientist of this project, and I will give this talk on behalf of Puli Space Technologies. So next slide, please. So let's talk about a bit neutrons on the moon. So on the lunar surface, we have a mixed radiation field, as you may be already aware of. And this mixed radiation field is actually varies strongly spatially and temporally, so both in space and time. And we have this mixed radiation field because we have, of course, the incident high-energy galactic cosmic rays continuously bombarding the lunar surface, the lunar regolith, penetrating into and colliding with the atoms of the lunar regolith, as you may know. Of course, these nuclear interactions create albedo or secondary neutrons, which are scattering around, losing energy inside the lunar regolith, and many of them at the end leaving the regolith upward in an upward direction, and it could pass through our spacecraft, lander, rover, or even payload instruments. So the energy spectrum, or the energy distribution of these neutrons leaving the lunar surface, is at the end a characteristic to the local subsurface regolith composition due to this continuous many interactions, scattering, which is basically makes neutron spectroscopy, this field, very interesting for lunar exploration. And of course, neutron spectrometers, a very useful tool and devices to characterize the lunar surface composition. And we have to highlight here that there is a very strong dependence on the hydrogen content, water and hydroxide content of the lunar regolith, because of course the hydrogen nucleus, the proton, has a very similar mass with a similar mass as the neutrons. Therefore, they can lose a lot of their energy colliding with the hydrogen. Therefore, we have a very strong dependence on the hydrogen content. Next slide, please. So this is why we at Puli Space Technologies we started to study the neutron interactions, the neutron environment of the lunar surface. So and the best method for this to run and make accurate realistic modeling of these radiation environments with the Monte Carlo particle transport simulations. And of course, there are many well-known, reliable physics code to do this kind of Monte Carlo simulations. So we have started this scientific study, and we got many neutron spectra, as you can also see here plotted. So basically, this is the neutron flux, neutron differential flux in function of the energy of the neutrons, which are leaving a regolith. And we are detecting or counting these neutrons above the regolith, where we can place a lunar rover and or a payload instrument. So, and as you can see here, as we increase the water content, water concentration of the regolith, we have more and more, so higher thermal neutron flux, which is the lowest energy neutrons we can have, thermal neutrons. And at the same time, we have lower and lower epithermal neutron fluxes, which are the moderate energy neutrons, let's say. So together, the higher thermal and lower epithermal neutron flux indicates higher local concentration of hydrogen in the regolith. And the ratio of thermal and epithermal neutrons actually can be is the best, one of the best quantity to measure when we want to find the hydrogen or water in the soil on the lunar surface. So and of course this measurement principle has been used already. So this is not a new method, but so far it has only been used from lunar orbit. For example, instruments of the Lunar Prospector or Lunar Reconnaissance Orbiter have been already measured neutron spectra and thermal and epithermal neutron count rates from lunar orbit. But these results in a very low resolution maps of the lunar surface, where the hydrogen and how the water is distributed on the surface. But this measurement principle is not yet used on the surface, so on ground level. Although everyone is very much interested in the water distribution and water deposits, water resources on the moon. So this is our main motivation to actually, that's why we have started to develop our own payload instrument, which addresses this topic. So next slide, please. So here I would like to introduce you the Puli Lunar Water Snooper, so the payload instrument I just mentioned and what we are working on right now. It has very small dimensions, 10 by 10 by 3 centimeters only, and it will have less than 400 grams weight. It runs on low voltage and low power, so less than 4 watts, and it needs on less than 12 volts. It's a low-cost, commercial, off-the-shelf, component-based payload. And as particle detectors, we are using modified off-the-shelf CMOS image sensors, actually scientific CMOS image sensors, but I will also talk about a bit later. And this payload instrument is supposed to cover between 1 and 7 square meter area per measurement, down to a maximum of 1 meter depth in the lunar regolith. So this is the area and volume basically where we can measure on average the average hydrogen concentration per measurement. The data acquisition is approximately will take around 30 minutes per location, but of course this is highly depends on the actual local radiation environment and the hydrogen concentration we are measuring in the soil. And the ideal hostcraft for our payload are small lunar rovers, and of course. And I will also show you soon why I said this. And of course, landers can also host our payload instrument, but then we'll only measure neutron fluxes, and so yeah, mounted on a lander is not really optimal for mapping or searching for water deposits on the moon. But it can be also an option. So next slide, please. Yes. So this, what you can see here is actually the data products of PLWS, Lunar Water Snooper, and so how the data coming from our instrument will look like in the future. So probably it will be mounted on a small, let's say 5 or 10 kilogram lunar rover, which discovers area and takes a few hundred meters of path, and the PLWS will measure, monitor basically the thermal neutron flux, the epithermal neutron flux, and the cosmic ray, the background particle fluxes, continuously along the way of the rover. And based on these measured quantities, fluxes, we can obtain directly or indirectly the water concentration or water equivalent hydrogen concentration measured across the path of the rover or in function of time. So basically using our instrument, the lunar subsurface water resources could be mapped spatially with a very high resolution and very good accuracy. And basically with this, we are addressing scientific goals of the NASA Artemis program, and also an essential need of the in-situ research utilization community, as everybody, many institute organizations, agencies, and companies are really interested in the water distribution, water deposits on the moon. Next slide, please. So how the project started, a bit of a history, and I will talk about the project timeline. So the whole project started in 2020 April, when NASA actually had a challenge, announced the challenge called Honey, I Shrunk the NASA Payload. So this was via the Heroics platform. And we already had some ideas, so we started to work on it, and we have submitted our ideas. Actually, the goal of this first challenge was teams had to propose ideas for miniature payloads, which will fit in this very small volume and very and has to be very lightweight, so compatible with small lunar rovers, which could be probably potentially used on the commercial lunar payload services missions of NASA. So we submitted our idea, and we won the first prize of this NASA challenge in 2020 July. And after this, we have been invited to the sequel challenge, among with many other teams. In total, 14 teams had basically proposed a plan how they will develop their idea and build their prototypes. So we have also won this second sequel challenge. 4 teams have been selected. So Puli Space Technologies also have been selected, and basically we are now supported by NASA for a 1 year of development period. And the goal of this sequel challenge is to deliver 3 working flight-ready prototypes to NASA Jet Propulsion Laboratory until 2022 January. So the schedule is really tight, and we are working hard to meet this deadline, but we are confident that we can develop a functioning neutron spectrometer, basically what we proposed. I'm introducing here, and yes, and in 2022 January, we will send our flight-ready prototypes to NASA, what they will test, and if they if these payloads pass the qualification test at NASA JPL, they will integrate it in a lunar rover and lunar lander, and they will send it. They are planning to send the payload either to Rainer Gamma, which is an equatorial landing site, in 2023, or to Schrödinger Basin in 2024, which is a polar region of the Moon. So we are yes, and important to mention here that we have already manufactured a prototype, but I will also show a bit later. And now we are in the middle of the functional testing. So next slide, please. Yes, I have to mention that, of course, this is not only our company, Puli Space Technologies, who is working on this, but there is a whole large collaboration behind this project. So Puli Space Technologies is responsible for the system design, integration, and then basically the scientific R&D of this project. But of course, the funding, but of course, there are other partners, collaboration partners, like we have partners, companies who are working on the hardware design, some other companies who are responsible for the manufacturing, and we also have a nuclear physics institute for testing our payload. NASA providing the funding, and they will be the first user of this payload. But of course, we are not just building and developing our payload for this challenge and just for NASA, but only we would like to have this for the whole in situ research utilization community and basically commercialize this product in the future. As you can see, our collaboration is already quite large, and I have to say that it's still growing. So we will have soon other new collaboration partners in this list. Next slide, please. So as I mentioned already, we are using image sensors as particle detectors. So this is the novel idea of this payload instrument. We have these scientific CMOS active pixel sensors, quite large, 2 by 2 centimeters, and we have modified them, developed a special sensor coating to be able to detect neutrons efficiently. So, and we have 3 sensors within the payload instrument. We have one sensor for the thermal neutrons, one sensor for the epithermal neutrons, and of course one reference sensor just to measure the cosmic ray background and gamma background of the lunar surface. And basically from the signals and data of these sensors, we can obtain the, after some calibration, we can obtain the hydrogen or water equivalent hydrogen content of the lunar surface on a specific spot. And what you can see on the photo is the manufactured engineering model of PLWS, which is almost ready to be irradiated with neutrons. So we are in the middle of the functional testing, but it's up to now it's operational and functional, and we are on track. Next slide, please. As I mentioned, we will irradiate these engineering models soon with neutrons, but we already had our first neutron test, the proof of concept test, and I'm showing here the most important results of this proof of concept test. And basically, we have successfully demonstrated the neutron detection technology behind this instrument and the flux monitoring capabilities using an americium beryllium neutron source at CERN with modified commercial off-the-shelf cameras. So we have both COTS cameras and modified them, added this special coating, and we could detect both thermal and fast neutrons So here you can see a photo of this setup, what we have done in collaboration with the CERN, CERN Radiation to Electronics Project and CERN Radiation Protection Group. So in this, now we of course would like to thank them to their contribution. And and you can see here two images acquired by the camera, two parts of two frames, and on the top you can see a thermal neutron induced image basically, and below you can see a fast neutron induced particle track. So we can clearly differentiate with these special modified cameras between thermal and fast neutrons, and we can count them, and we can get the count rate. So on the plot, I've plotted in function of source camera distance the count rates of the different cameras, reference camera and the camera which has been modified and coated. And we can clearly see that as we increase the source camera distance, the flux is changing the same as the count rate is changing and decreasing the same as the flux is changing in our simulations and as it should. So the flux monitoring capability has been successfully demonstrated and proved. Next slide. And with this, I would like to thank you for your attention. And if you have any question, please let me know. And if anyone is interested in more detail in this measurement or payload or project, then please send me an email. Thank you very much.